Okay, we're off to start day 5. Welcome to all of you that are with us today. We have a number of good sessions coming up. First up will be Michael Heroux talking about software engineering best practices. No matter how much you optimize and speed up your codes, most of you are part of a team and will be followed by others after you leave the project. So it's really vital that you follow good software engineering practices so that the work you do will live for a long time. So with that, Michael, if you're ready, we'll turn it over to you.
Perfect, great. All right, let's get started. Thank you for the introduction. Thank you for the opportunity to speak. I'll share you some of my thoughts. First, a bit of an acknowledgement to the U.S. Department of Energy and Sandia National Labs who pay my bills, so I appreciate their support. I thought I'd give you just a brief bit of background on my experience. So I spent about the first 10 years of my life at Cray Research working in scientific software, first in math libraries, then as an application analyst working in the fluid dynamics group, and then working on algorithms for the so-called MPP systems, the Cray T3E in particular. And then joined Sandia in 1998, and in that period of time I've worked again on a lot of scientific software projects, primarily in a leadership role. I've also done a fair bit of work in community benchmarking, the HPCG benchmark, and then also trying to work on the incentive systems in our communities to exhibit the value of software as a discipline, as a value proposition of its own within our communities, so that we can give credit to people who do good work in this area more than perhaps has been in the past. And concurrent with all that, I've been a scientist in residence at St. John's University in Minnesota, and a lot of my work has been with students doing scientific software research and development there. And so all of these experiences have informed my perspective on this particular topic. So here's a bit of an outline. I want to give you my perspective, and then I want to try to motivate why we should care more about software best practices, give you a brief summary of what I've called in the past barely sufficient software engineering, and then talk about some lightweight small team management, agile methodologies, planning, and then I want to give you 2 practical techniques that we have found useful in recent years. And then finally, 2 things, how to introduce best practices or better practices into your own team, a strategy for that. And then also a last message that I think is really important as a way of building community and building a sense of personal expectations as we produce scientific and use scientific software. Okay, so what is my perspective? I am not a professional software engineer. When I'm going to talk about opportunities to improve, I'm more like a scarred veteran than an expert. Having been in this field for many years, I've experienced a lot of things, both good and bad, and I'd like to share my perspectives on those experiences. And then regarding software tools and processes and practices, I'm more like a carpenter. I find a good tool and I get excited about using it. I still am active in development, and I get excited about things. And so I want to explain to you tools that I found that are useful and important to me. All right, so let's move along. So why should we care about better software practices? We can certainly care about them from a holistic point of view and thinking that these are things that we should just do better. But there's actually, I think, a growing scientific demand for better practices, and it comes from a general awareness of insufficient transparency and reproducibility. If you read the New York Times or you're familiar with the Center for Open Science, you may have seen this article on the reproducibility of psychological findings. Now, it's not computing related, but it does speak to the general notion that we don't know as much as we think we know when we do some scientific studies. And that was the the gist of this article in the New York Times. And I used to show this and tell people, well, we would not do well in the computational sciences if a spotlight were shined upon us. But it was hypothetical. But in that, since then, there actually has been a very interesting case study, and I encourage you to go and read about this article, or read this article and read about this case. In Physics Today, there is an interesting article about the war over supercooled water. There are two teams, one led by De Benedetti at Princeton and Chandler at Berkeley, who were disputing the behavior of pure water just above what's called the homogeneous nucleation temperature. De Benedetti said two possible phases, low or high. Chandler said only one phase, high. This dispute went along for many years, and it was not resolved until finally Chandler in Nature said that LAMMPS was one of the codes that was being used for this. The codes are standard and documented with scripts freely available upon request. De Benedetti with a colleague Palmer said, "Send us your code." After some coercing via Nature, the publication, they finally received the code. Palmer did, and then quickly discovered a bug or a feature right in the Berkeley code. It turned out to be something that made the code run faster, but was maybe a little less real or realistic in what it was trying to model. So when Palmer replaced it with a more standard approach, he then obtained from the Chandler environment similar results to what the De Benedetti results were back in 2009. Unfortunately, it took 7 years for this resolution to occur. And I won't read this quote, you can see it there. But the essential loss to the community was that here we have a span of 7 years. Some people's careers were, strongly and negatively impacted, and there wasn't a culture of transparency or reproducibility in this community, and so these are some of the stakes that are present as we try to move forward. As a result of, say the cost studies, that we just saw in the New York Times and the De Benedetti, although I'm not sure that has really necessarily influenced things, it's a fairly recent phenomenon. But there is a general sense in the publications that we need to increase emphasis on transparency and reproducibility. And just briefly, transparency simply means that you make available to others the details of the process that you used to do your computational results. It doesn't mean that you necessarily give the code, so it's a weaker form, right? It's a necessary but not sufficient condition for reproducibility. Reproducibility, on the other hand, is this general notion that if some results are published, somebody else can attempt to, first of all, reproduce them using the author's environment, and then do what's called replication, which is getting consistent results using a different experimental environment. So just a little bit on those two terms. So one example of this is within ACM TOMS. At the time that I was editor-in-chief of TOMS, I initiated this what is now called reproducible computational results effort. The idea here is that you assign an independent reviewer who's not involved in the quality of the scientific result of the paper, but whose only job is to go and look at the results and confirm that they are what the author intended them to be. So this is one example of where transparency and reproducibility are being promoted and encouraged in the community. Also in the supercomputing conference, in the last few years, there has been an effort to create what are called appendices, artifact description appendix and artifact evaluation appendix, that give authors an opportunity to exhibit the rigor that they have put into making their results reproducible by somebody else or more trustworthy. And if you want to get some more details, there's a link here for that. So So those are a couple of, there are many other examples I'll get to in just a minute. But I do, since this is the Petascale Institute presentation, I also wanted to talk about what you could do if you can't repeat experiments or do similar experiments because of accessibility. What can you do to improve trustworthiness? And so here's an example. So suppose you compute a Heroux calculation using 5 million core hours on Mira, the system at Argonne National Lab. You submit your results for publication, and during the review process, a referee questions the validity of your results. What options are feasible? Well, could the reviewer rerun your code on a laptop or a cluster? Clearly, probably not, because of the size of the problem. Could the reviewer rerun your code on Mira? Probably unlikely, unless they have the same kind of access and allotment to hours on the system that you had. Or can you rerun your code? Again, very undesirable, because it would use up an additional extra amount of computing that you would prefer to use doing new results. And then another option is your results are rejected or your results are accepted, but with a risk. None of these are really good options. And so one of the things the artifact evaluation appendix within supercomputing is doing is trying to promote the notion of meta computation. So you can think of, if you describe the software environment you're using, that's metadata about your computation, what you did. And that's all really good. That allows somebody else to potentially repeat your experiment or build on your experiment and use it as a starting point for their own work or adapt it. But meta computations are small little computations that you do inside your code, perhaps within the preamble before you start executing the real job, that allow you to test whether your computations are sane, whether your computing environment is sane. And we encourage people to look at things like, for example, you could pass in a synthetic operator, say with a known spectrum, a known rank, test invariant subspaces, look at compute conservation principles, things like that. And so this is a way of trying to address reproducibility at scale. Just as a simple example, I mentioned I've worked on the HPCG benchmark code. We have a few meta computations in that code. One of them is that we know that our linear operator is symmetric, and so one of the first things we do is we generate two random vectors, x and y, and then we make these computations. Since the HPCG benchmark has a linear operator apply method, essentially a sparse matrix vector multiplication, we're simply using the kernels that are already going to be exercised in the benchmark execution. And so by doing that, we can do these two computations that require symmetry of the operation, of the operator, and then do the simple test. It doesn't take a lot of time, but it makes sure that our execution environment is saying that if the benchmarker ran this and they made a mistake in their implementation of the optimized sparse matvec, that they could get, we would be able to detect that. And so this is the kind of thing I'm talking about with meta computations. So the main point here is that if you haven't experienced it already, reproducibility requirements are coming. I see, and others do as well, see that there's an expansion in the expectation that results that you put in your paper should be reproducible in some, and the degree of reproducibility, the rigor of that can be ratcheted up over time as a community matures in its abilities to do reproducible computations. And so this is, if you haven't experienced it, it's a heads up that this is happening. Gregory Furston has a very nice webpage talking about the conferences and reproducibility. It's a worthwhile resource to look at. I mentioned the ACM. It used to be called replicated computational results. There was a discrepancy in terms that has now been resolved between ACM and the computational sciences community. That's been fixed, and so now we call these reproducible computational results. ACM also has a badging system, so that if you produce results that have been repeated, then you can get a badge on your paper, and these badges provide, again, an incentive to authors. I'm also now part of an NISO community or committee on reproducibility and badging. Now we're expanding the discussion of reproducibility and badging and consistency across publications. Publishers include ACM, IEEE, Figshare, STM, Reed Elsevier, and Springer Nature are a few of the team members on that. So just then, this is a motivation, if you didn't have one already, about why you should care about reproducibility. All right, so why is something about reproducibility and transparency in a talk on software best practices? It's because if we're going to make reproducibility affordable, we need to invest in software engineering practices. We need to make the cost of producing high quality software and sustaining high quality software affordable so that we can be competitive in the scientific sphere, producing results. And so, here's just a simple schematic, right? So transparency and as we increase transparency and reproducibility requirements, that demands improvements in productivity and sustainability, investments in that area, which then in turn enable us to do a better job at transparency and reproducibility. So I've often heard the phrase, I'd love to do a better job with my software, but I need to either get a paper submitted, complete this project task, do something my employer values more. And what we're trying to do with these efforts to elevate the value, the incentive system support for efforts in productivity and sustainability. And so it's very important to make scientific and computational science healthier, more holistic in its approach to getting work done. You may have heard the phrase better, faster, cheaper, pick two of the three. So here's a scenario, for example, you're behind in developing a sophisticated new model in your software that you want to use for results in an upcoming paper. And so you have a choice, right? You can pick two of the three things. You can develop a simpler model for the paper. You can set other work aside and spend more time on development, or you can ask for an extension on the paper deadline. So those are all examples of the better, faster, cheaper trade-off. And often you can blend, right? Compromise a bit on two or all three of them. Other options are develop the sophisticated model, but don't test its correctness. Develop it, but don't document it or check it in. The testing its correctness or not is related to risk. Are you willing to take the risk that your result might be wrong? If you don't document it or check it in, that means that you've now created something called technical debt, which is you have a piece of code that you've checked into your software repository or put it into your overall collection of software, and it's not sufficient for easy sustainability. And none of those are really good choices. So what I want to suggest is that, okay, maybe we can't fix how things are today, but let's say you were to take a small slice of time and put it into improving your developer productivity. Do a little bit better job of, say, learning things like a debugger, or doing more frequent check and testing of your software. And if you can do that, you can improve your productivity of the development team and see some benefit from that. And usually see that in a fairly short span of time, maybe 6 months later. Then you'd be able to do all three of the things that we talked about. You'd be able to get the result done with a sophisticated model on time without putting in evenings and weekends. And so improving developer productivity is a way to get fairly short-term, medium-term impact on your ability to produce scientific results. Another way of improving productivity and sustainability, or of improving your ability to do science, is to invest in sustainability. So do a better job of documenting your code. Adopt a programming a standard for source code formatting, things like that, that improve the sustainability of your software. Now, you're not going to see the benefit of that necessarily right away. That's something that will pay off in a longer time scope, but it will pay off in very powerful ways over that longer time scope. And so that's another way of being able to do better, faster, cheaper, get all three in a long-term sense. So just a little bit of a question for you. So which of these enhance reproducibility? Code written by a first-year untrained grad student, tuning for high performance, dynamic parallelism of modern processors, better software testing, source code and version managing, and so on. So I can't see your hands, so I can't ask and get an answer of who thinks for code written by a first-year untrained grad student would enhance reproducibility, but most of you would probably answer it would not. And that's obvious, but we have a lot of first-year untrained graduate students. And so we need to, if we want to improve our chances for reproducibility, we should acknowledge that and try to put in place a way to address that risk. Tuning for high performance. Maybe that's not so obvious, but it's actually one of the, if you're familiar with Steve McConnell is to me, a very gifted software engineering instructor, teacher, thought leader. And he has a table in one of his books called Co-Complete, the book is, and he shows 8 quality metrics. And he looks at, as a matrix, how does one impact or influence other quality metrics. And one of the quality metrics that he has there is efficiency, which is essentially a superset of tuning for high performance. And in his chart, he shows that tuning for efficiency only positively influences itself, and almost all of the other 7 quality metrics, correctness, usability, the other code quality metrics, tuning for high performance decreases those quality metrics. And so it's actually counterintuitive maybe, but tuning for high performance can often have a negative impact on code quality. Dynamic parallelism is another thing that's very difficult. If you know that floating point arithmetic is not associative of, and so you can A plus B plus C could be a different result than A plus C plus B, and so that's a challenge when you have dynamic parallelism. All of the other 4, of course, tend to enhance or improve reproducibility. All right, so what are some software engineering basics? If you've never thought about software engineering before, I wanted to give you at least a little bit of information that could be useful to you, and you could maybe go off on your own and take a look at some of these ideas. This is actually based on a paper I wrote about 10 years ago entitled Barely Sufficient Software Engineering. And I looked at it, and the 10 principles are actually, maybe with a little bit of time translation and adaptation, I think are still really solid. So manage source code, and nowadays GitHub, GitLab, if you're using GitHub, the GitHub desktop client are really, really powerful ways to manage content. I lived in many years in doing software development engineering before these platforms became available. The availability of these platforms has totally changed the quality of work that we can do in managing our content with a very low barrier to being able to become good enough at it to realize the effectiveness of these tools. The value can't be overstated, in my opinion. Similarly with issue tracking. GitHub issues are very great lightweight tool for managing tasks and work tasks. And then Jira, if you're in a larger organization or want to adopt something that's really ambitious, Jira is part of what's called the Atlassian tool set, is an excellent tool, very powerful, typically harder to get to use effectively if you're just getting started, but it is a fine tool. Both GitHub Issues and Jira support something called Kanban, which I'll get to later on in the presentation. Okay, and then setting up communications, Slack, Confluence, mail lists, and so on. These are all very important activities and tools that allow us to communicate. Checklists I'll talk a bit about. Source-centric documentation, read the docs and Doxygen are 2 excellent tools. Configuration management, CMake is a great tool for that. Writing tests first, using them for integration testing. The use of pull requests or merge requests. Pull requests are a GitHub thing. Merge requests are a GitLab thing. These are all very useful things. Selective use of pair programming. Doing formal releases using what's called semantic versioning, where the first values, so it'd be like 12.2.3, 12 is the major version. Only certain things can happen in a major release. Minor and sub-minor are other versions. And so these are all very useful things to do. And then the final thing is continual process improvement. And I'll talk a bit more about that. But you could take this page right here, this slide right here, and if you haven't done software engineering, there's plenty of content, hooks in this page right here that could allow you to go off and learn a lot on your own and get started down the path of improving how you do software. I want to talk a bit about small teams, because I'm guessing many of you work on small software teams, and you may work in teams where you have a stable group of people who are persistent in their efforts, and then a set of probably students or postdocs that are making their way through the organization. And so you have the senior staff or faculty. They're a stable presence. They know the conceptual models well. They spend less time writing code, and in fact, sometimes are even fuzzy on the details. Junior staff or students, they're transient. I think it's really important to recognize that they have a dual focus. They want to get science results as part of the team, but they also have to prepare themselves for whatever the next thing is. And they often have this staged experience. They're new, experienced, and departing. And they're learning the conceptual models. Often they end up writing a lot of the code, again, in my experience, and they know the details of it, even if they don't necessarily know the conceptual models as well as the senior staff. Large teams, if you're part of a large team, my experience with large teams are often a composition of smaller teams. And so you can take the things we're going to talk about with small teams and then add to that a layer of what's specific to large teams. I won't get into that in this presentation. So what are some of the challenges with a small team? You're ramping junior members up, and you're preparing for departures of experienced juniors and managing this dual focus of them getting work done for you as a senior member, and then also preparing themselves for getting out the door. And this is, in a sense, a diagram of the basic research team member life cycle. I won't go into detail right now. Two of the things that I found to be really effective as software engineering practices is the use of checklists and policies. I have checklists for new team members. I keep a master checklist. And then from that, one of the very first things I do, say, is I bring a student on board for the coming year, is I create a customized checklist for them. I create a GitHub issue with that checklist embedded in the issue. And then that gives the student a schematic of what their early efforts are going to be on the project. And they get to go literally check each item on the list, check it off as done. And there's real value for them seeing the progress they're making. It's tangible. It's all online, in GitHub. And so both of us can see the status of their activities. If they have a question about one of the items, we can chat back and forth in the comments section of the issue. And at any time, we can update that and modify it as needed. Similarly, for a departing member, about 9 months before a student is leaving, I create from a master checklist a checklist of everything they need to do before they leave. Includes things like ordering cookies for their defense because no one else is going to do that for them. So even down to those littlest details, most of it's bigger, important things. But I think these checklists are great for managing transitions. And if we are going to start up a new project effort, say, one of the first things we do is we create a checklist of all the things that we want to do as we ramp up in this new topic area. In between arriving and departing, we still need some kind of guidance on behavior. And this is where policies, team policies end up being a really useful tool, in my opinion. And we've created a set of policies. Policies are essentially expectations on the behavior of team members. It can often be a statement of best practice, but they tend to be less sensitive to time, statements of broad values for your team, and the process of building the policy statement is actually a team building exercise. And maybe from year to year, going back and revisiting your team policy, and so that new members can be part of the conversation. Well, should we modify this? Because often these things can change, or you get a better sense of how to state a policy that might be a policy item. And so I find these to be really useful, lightweight techniques for managing small teams, especially teams with transient members, who are arriving and departing over time. So, here are some questions. What do you want a new team member to know? What policies do you want to have about ongoing work? What do you want to make sure happens before somebody departs? You can discuss this if you want, and put it into a Google Doc in a brainstorming way, and then post it to your team's, say, GitHub organization if you have one or something like that. So here's just a small text, I know, but I just wanted to give you some example. So my team I call Collegeville. We're in a tiny area in Minnesota called Collegeville Township, and so it's a nice name. And so these are the team policies. So one of the first things I do in a policy is I point to institutional policies. Almost every institution has a policy, and so my team members should know about that and be aware of the things in it. Then we have a policy about initiation, transition, and exit events should be guided by creating and following an event checklist. We have policies about where information should be, what kinds of repositories, and so on. This is for a student of mine who recently graduated, Neil Lindquist, and this is his initiation checklist, all the things that I wanted him to do as a part of that. And you can see that then this allows us to actively manage his initiation into the effort. And so there's just a couple of examples that you might find illustrative. So let me pause here, see if you have any questions or comments.
There are a couple of questions that have been posted.
Can you all still hear me? Great, go ahead.
Is there anything inherently better about GitHub Desktop Client over the command line version, referring to your slide 26?
Yeah, it's a great question. So it depends, right? If you are a command line person and you are using Git commands on a regular basis, the command line is perfect. I've done that for years. I like it. However, I have found over time for certain kinds of workflows, using the desktop client is easier because the cognitive load associated with doing simple actions using the GitHub desktop client is much lower than having to do it by command line. I can see everything. I can see the state of my repository in the GUI, all the files that have been changed. I can look at the diffs all in just a single interfaces. And for me, that's really useful. I really find that valuable. I don't use it, so when I do development in one of my software projects, I tend to use the command line. However, I use also GitHub for doing a lot of content management. That's about web pages and wikis, using its web generation Jekyll generation content. And there I really find the desktop client very useful. So both are useful. I would also say if you're relatively new to Git, and especially distributed source management tools, the GitHub desktop client is a simplified model. It doesn't expose all the capabilities, at least in the first page. It doesn't expose all the capabilities of Git and allows you to work with it with a simpler mental model that may be the most advanced model you need as a developer. And so anyway, those are some of the trade-offs I see.
Okay, a second question. Suggestion for problems must be run and submitted along with CFD works. General recommendations, please.
Say that one more time, please.
Suggestion for problems must be run and submitted along with CFD works.
I'm not sure how to parse that. Sorry.
Me either. Maybe Julio can rephrase. That's
yeah,
it.
Please do. Okay. If there's a chance to rephrase that, there's another pause coming up, and we can try that again. All right. So I also want to talk a bit about Agile methodologies. Now, Agile is this big term of often fuzzily defined, includes a lot of complementary and competing approaches. But generally speaking, Agile methodologies as a collection approaches to managing a team and managing technical activities, I think is very compatible with the scientific software development and use efforts. And so I think it's a combination worth pursuing. So what is Agile? Well, it's not really a life cycle model. It's an approach to managing the activities of a software team, and it tends to have iteration and incrementation as a part of how work gets accomplished. Sometimes people define it informally and often, I think, irresponsibly incorrectly as I don't write documentation. I think that's a little scary depending on the situation. I don't write formal requirements or design or test. Again, I think that can get you in trouble. And so really Agile is not an excuse to do sloppy work. So it's actually, when it's applied rigorously, is a serious disciplined approach to doing software, even though it can be very lightweight. Okay, some people think Agile is synonymous with Scrum. Scrum is a really nice workflow. It's used by roughly 80%, depending on whose stats you look at, 80% of the professional software teams in industry, and they swear by it, and it's very attractive. However, I think for teams that are just getting started, and even for teams that are mature in their software methodologies, Scrum is probably not the right approach for most teams. I tend to prefer Kanban, especially for just getting started. Concepts are simple. You can add to it. And so I prefer, so a lot of people, if you ask them, they say they do Scrum. And then if you get into the details, there are a whole bunch of practices associated with Scrum. They'll say, yeah, we do Scrum, but we don't do this part of it, or but we don't do that part of it. And so it's called Scrum but. Kanban is very simple. It's easy to do it, at least somewhat rigorous, or at least to do the practices even if you're not great at them. And so I find it better to do something called Kanban and versus Scrum but. So why Agile? Again, lots of things that are compatible with scientific software development. And I'll get into those in some detail here. So what's getting started with Agile? So Agile principles are not hard and fast rules. You can try adopting a few of them. Kanban, in my opinion, is the best way to get started. And so we'll go through a little bit of Kanban. So what's the notion of Kanban? Kanban is about, and central to Kanban is what's called the Kanban board. And it's essentially columns of tasks, activities that you need to accomplish in order to get your work done. And so it's simply that. The column that tends to be looked at the most is the column that is called in progress. These are the tasks that you're actually working on at the moment. And the discipline of Kanban is to put a cap on the largest number of tasks you can have in progress and do no more than that number. And why it is useful and that capping is important is because if you're not making progress on your in-progress tasks, it forces you to look at what are the inefficiencies in my system. Why am I not making progress? Why is my team not making enough progress on the in-progress tasks? And then you can look at it and say, okay, we need to improve how we're doing our work in this one particular way because we're not getting this task out of the in-progress column into the review or the done column. And so that discipline forces you to look at where you're inefficient and ineffective in getting things done. So this is a basic Kanban board. As I said, GitHub Issues using projects supports Kanban boards. Jira natively supports Kanban boards. There are lots of other tools. I'll show you a list in a moment. But basic Kanban is you have a backlog. And this is a list of any tasks that you think you want to get done, even if they're somewhat speculative. Maybe you won't get to them. And in the backlog, you put everything that you possibly want to work on, brainstorm, or well-defined. And then a second column to the right of that is called ready. These are things that are, in a sense, part of your backlog, but they're well enough defined that if you had a slot and set a time to actually take on that task, it's well enough defined that you could pull it into the in-progress column and get going on it right away because it's not vague. All its predecessor requirements are done. all the dependencies are complete, so you could actually get to working on it right away. In fact, you could move it into your in progress column if you had not had reached your max number of tasks in the in progress column. In progress are the things you're working on right now. A really key part of Kanban is that work in the in progress column is pulled. In other words, the owner, the person who's going to do that work, has to agree that they're taking that task on. It's a very powerful mechanism. And in particular, if you were, say a student and you had an advisor who tends to throw a lot of things at you, things to do, by having a Kanban board and having a list of the things that you're working on, and now your advisor comes to you and says, hey, I want you to take this other piece of work on, you can sit down with your advisor and look at the in progress column and tell your advisor, okay, you want me to do this new thing and you want it done now. Which of these other items on my in progress column do you want me to set aside? It's okay to set things aside, right? Kanban is meant to help us, not meant to be blindly followed. But it drives that conversation to prioritize activities. And the outcome of that conversation could be, well, everything in your in progress column is actually more important than what I asked you to do. Put it in your backlog. Okay, then done is a list of completed tasks. It's actually a really important column because it allows you to look to have a record of your activities. It allows you to do things like computing your velocity, which is also very interesting. As you get good at right-sizing tasks and making them about the same size, you can actually use your velocity, which is the rate of completion of these tasks, as a way of seeing how well you're doing overall. So there are also some other interesting columns you can put in. One is waiting on advisor confirmation. So if something gets put in that column and sits there a long time, it highlights that there's an impediment to getting things done. So that's some cool things about Kanban. Personal Kanban, I won't go into detail, but there's a lot of great stuff here. In this book. I can't promote the book, but I found it useful. What tools can you use? I already mentioned you can use the traditional ways, a wall or a whiteboard or a blackboard. There are lots of software-based tools I mentioned. Trello is one I use personally. It's available on handheld and tablet devices. It's a great tool. And then, as I mentioned already, Jira and GitHub issues. And I just mentioned this in progress concept for you. I really think it's useful. So please consider that as something to in your workflow as well. If you want to building on Kanban, here's a link to a web repo that has some details that you can consider. And here's just an example from the Collegeville org, for example. Here's our backlog, our ready, in progress, in review, and done. In the in review stuff is where you think you finished something and maybe you have to give it to somebody else to take a look at it. And then they may send it back to you, but then eventually we'll get into the in done. And again, let me move along because there are some other things that I'd like to get to. Okay, let me just briefly pause here for any questions or comments. Is that one question rephrased? All right.
There is a question. Kanban looks very similar to Trello, which you also said that you use. What advantages do you see of one over the other?
Yeah, so Kanban's a methodology. Trello is a tool that implements Kanban. Trello might be able to do any other things too, but out of the gate, when you set up a Trello board, it's essentially a Kanban board, or can be used that way. So that's the relationship between the two. So I use Trello to manage my own personal tasks and do it in the form of a Kanban board. All right. Let me move on to, go ahead, please. Okay, I'll move along. I want to talk a little bit about planning, because I think in my experience, this is another area where scientific software teams don't do as good a job as they could. And it's actually an area ripe for improvement. And in fact, my experience is that people who write scientific software, they're the main source of their requirements is the proposal that they wrote to get funding. And that's the level of detail of the requirements for the software. And so they basically go from that proposal and then start writing software. And that means that any requirements, the finer grain requirements, any kind of analysis or any kind of design work is actually being done in the software. And that's not the right place to be doing it. You shouldn't be working out all of those upstream activities in the software itself. And so just to illustrate this kind of behavior is, I've seen this in many efforts myself, is the bottom, the horizontal line is time. And over time, a team starts to plan, but they do very little planning. But what they really want to do is get to writing code. And so they start writing code. That's the white portion, getting results. And it feels really good. And then over time, they find they have to do more planning because they didn't really do a lot of work in designing their code or writing down the requirements and getting those clear. And over time, the amount of time they spend planning has to increase because the code base is really difficult to work with. And also over time, what happens is they have to start to do recoding and porting to new platforms, and that takes more time. And eventually, the amount of time spent planning and recoding and porting consumes the entire time, and you essentially end up abandoning the project. And that happens fairly often in my experience. It takes 10 years maybe or more for you to realize that, but it does happen. I would offer an alternative where you spend 100% of your time, very short length of time, in planning. Get some of the early stuff nailed down, and then you can eventually reduce the amount of time you spend planning and get to a sustainable software base that's much easier to recode and port over time. These are notional, but I've experienced this in my life. I've had this experience of the first kind in my own work, and that's why I can say I'm a scarred veteran in this way. One other technique I'm finding very useful in our teams are called stories. And so stories are a lightweight way of gathering and then refining requirements for your software. And so a story is basically a template. You say, as whatever role you have, I want, again, what do you want to accomplish, what it is that you want to do, and then so that I can accomplish something. And so it allows you to describe what you want your product to do in a way that is very lightweight. And so the typical mode of defining these is you brainstorm on a whole bunch of user stories. Because they're single sentences, it doesn't take a lot of time to create them. Then once you have this brainstorm collection of user stories, you can start to go through them and refine them and try to scope them so they're similar sized efforts. And then you can start to prioritize them. And then all you really want to do before you start, say, a development phase is find the top ones that you want to accomplish. And then you turn those into more detailed definitions of how to get the work done. And so this is a very useful story. I've also appreciated, again, for scientific software, that a different version, what's called a job story, it's called when, and it describes a situation. I want to, again, you want to do something so I can accomplish a task. And so that's another form of this kind of stories that can be really effective. And what we tend to do is you can put these into a Google Doc, in Confluence, which is another Atlassian tool associated with Jira. You can create a table, and so you can collect these things. I would recommend a shared document of some kind so you can work collaboratively with your team in generating these stories, and then trying to winnow them down and come up with the highest priority, correctly articulated stories. And then this gives you a bit more detail about how you can scope and refine and prioritize them. You'll also often get some of them that are out of scope. You just say, no, this is a good idea, but not on the mark. And then go through this prioritization and choosing. Again, it's a very lightweight technique for trying to figure out how requirements should be identified and refined prior to doing design or software development work. Stories are useful actually in other settings. I found it useful for selecting tools, right? Selecting a team IDE. You can create a set of user stories about what you want your tool, your IDE to do, and then go out and look for one that meets those requirements. Setting up team policies, doing a group reorganization. Ask the team members of your team, what does this organization need to do for us, and set those out as user stories. So as a developer, I want my organization to do this so that we can accomplish this activity, that kind of thing. Okay, a little bit about documenting design. Just really a single slide here, I think. So when you start looking at literature for design and how to do design, there are all of these heavyweight things and ways of doing it. I would not recommend that to people just getting started with design. Instead, start using the tools that you know. We have a team who's done kernels for micro and batch laws, basically linear algebra subroutines. And just as an exercise, they wrote up what they intended the design to be in a LaTeX document with a few diagrams. It was very easy to do, took a few days. And then the powerful part of that is they then passed that document around to architecture experts, to language experts, to other people who could comment on the plan that they had. And they actually fundamentally redid the data structure design on paper. Whereas if they had gone to the writing of the code, they would have encoded their original design and then have to go back later and then either live with that design that in the implementation or have to go do a bunch of rework. And so it's a very powerful way, again, low cost way of overall saving time in your software engineering and development efforts. Okay, so I've given you a few ideas about better practices. I hope are better practices. How do you get there? How do you get started on this? And I love this quote, an adaptation of Martin Fowler, a software engineering visionary. Use iteration and incrementation only for projects you want to succeed. And we have to do that as we introduce new things, new ways of doing software into our development activities. And so I think the most successful way to introduce new ways of doing software, improving your practices, improving your processes, is to look for things that can be done incrementally. And in particular, you want to pick things that improve how you get your work done on the way to getting it done. You can't just take 6 months off and do a whole bunch of stuff related to improving process and practice and not get any science results out the door. So we have to do this in an incremental way. And you want to pick things where there will always be some overhead. There's no way around that. Introducing a new way of doing things always has some overhead, but you want to do it so that you can realize the benefit of the new practice in a sufficiently short span of time that improves your current activities and getting scientific work done. We use something called productivity and sustainability improvement planning. Again, there's a repo here that you can go to look at what we do here. We have a lightweight formal process for doing this that we've used on a variety of teams. Here are a couple of examples. MPI-CH is one of the premier MPI implementations developed primarily at Argonne, where they've used the PCIP process to help develop onboarding techniques for new team members. Exalt is a new effort within the US Exascale computing project that's bringing together existing codes, for example, the LAMPS code as an example, and bringing those together. And so they wanted to introduce continuous integration testing into their activities. And PCIP is one of these iteration and incrementation approaches to getting work done. All right, last thing I have is personal expectations, calling out the best in team members. We can have all of these practices at the team level, but there's also an element of personal expectations, calling out the best in our team members. Just a fun little thing here. Canadian engineers take this oath from Rudyard Kipling. They get this iron ring. I'm not sure how true this story is, but people say it was from the iron of a failed bridge. I don't think it's a true story, but it's fun to tell anyway. But anyway, so this kind of personal call to excellence, I think, is a really important element we often forget when we're trying to build software teams, and I think it's worth calling out. In particular, one of the things I like is this notion that there are a lot of people who commit code to GitHub. Okay, and GitHub reports statistics on who did the most commits, and some people take pride in their high ranking. But my pushback on that is, if you have a software team that is not disciplined in their in their development of software, if you show me the person who's doing the most commits, I'll show you that it's that same person who's injecting the most technical debt. And so we really have to be careful about the metrics we use to measure people's contributions to a software project. And I list a few other things that I think are probably more important and harder to measure perhaps, but possible to measure in our modern software environments. And then the last thing I want to mention here is for my own team, I lead the Trello project, a scientific libraries project at Sandia. I created some shelf magnets that have this image on it. And I want every person, before they sit down to do their work, and ask themselves, is my work traceable? Meaning, can I point back to the requirements that drive it? Is it in progress? Is it in a Kanban sense? Is it what I'm supposed to be working on? Is it sustainable in that I'm putting enough work into it that it'll live as long as I need it to live? And am I improved in how I do my work because I've been doing some studying and improving things overall? So wrap up, I think better software engineering is needed, if not for any other reason, because we are getting greater expectations for transparency and reproducibility, and we have to make that affordable to do. I gave you some set of barely sufficient software engineering techniques. This is all turnkey with the advent of GitHub and GitLab platforms. I think Agile makes sense for scientific software teams. It's very compatible with how a lot of scientists do their other work. And then these lightweight structured planning techniques can be really useful. Use iteration and incrementation for introducing new ways of doing your work into your project. And then try to come up with some way that's not corny. It can't be corny, but a way to call out the best in your team members. And I'll stop there and see if there are any other questions.
Yep, we do have a few. Thank you, Michael. I'm going to interject a question of my own or a comment for you.
Yeah.
Do you want to say something more about the better scientific software effort?
Oh, yes, I'm happy to. Yeah. So BSSW.io is a website. I had it way in the beginning of my presentation.
I know you referenced it.
Yeah, so BSSW.io is a new effort. It's been around for a few years. Here's the logo here, bssw.io. It is a portal for scientific software developers who want to both see some of the better work that's going on that's focused down on the scientific software, and also we would love contributions. So if you have a best practice, if you have some thoughts on how to do scientific software better, we would love for you to participate and write a blog article for us, or write what sometimes is called curated content. So we would love to participate, and we're engaging the entire scientific software community over time to create this portal that is available and usable to everybody. Thanks for asking that.
Another question relates to surprises along the way. Do you have any experiences you can share about adjusting the development plans on the go?
Yeah, that's a great question. So this gets a lot to what, say, methods like Scrum are about, and iteration and incrementation. I've hit all sorts of surprises along the way. Probably some of the ones that are most harmful is not spending enough time up front really understanding what I need my software to do. And I have this vague notion of what it's supposed to do, and I start writing it. I start with some basic assumptions, but as I produce the piece of software, I have to get into the details of exactly what it's going to do. And I realize at that point that what I needed to do is not what I originally thought it should do, but my total design and my implementation and the design are not going to support me in having it do exactly what I intended it to do. If I had spent a little bit more time up front, analyzing it and understanding its behavior, or prototyping, right? So there's this notion in software of a wicked problem. A wicked problem is a formal term, actually. A wicked problem is one where you cannot know the answer by just looking at designs and requirements. You actually have to do a bit of prototyping before you get some insight into what the final design would look like. And I would love to have spent more time, multiple times in my career, doing this handling a problem of design as a wicked design problem. A little bit of prototyping, go back to the design, and then write the real code. So that's one example.
Okay, one more. You talked a lot about teamwork, but what about someone who's working as an independent developer? What are good codes? What good practices for someone working alone?
Right. Yeah. That's a great question. There's a lot of content on that out there. There's this notion of what's called a personal software process, which is, how do you as a person, develop and then maybe use your own software. And the first step I would recommend is to write down your process. What are the tools you use? How do you use them? And how do you go from getting a good idea to actually producing a working piece of software? Can you write that down in maybe a page or two? And then look at that and try to then timestamp, well, how long does each of these steps take as I produce my software? And then if there's one that's taking longer, because I think our intuition is pretty good at telling us if something's taking longer than we think it should take, look at that and then do a study, a look. You'll go out and look for new ways to do that specific thing, whether it's debugging or do you need a better IDE. And there's a lot of information available on the internet that can help you, identify the possible 2 or 3 tools or 2 or 3 processes for improving your overall personal workflow. And if you have a specific question, send it out to Stack Exchange, Stack Overflow, and ask it, and you'll get some good answers back. So that would be my first advice.
I don't see any other questions, so at this point I'd say thank you very much, Michael, for a tremendous presentation. You got some nice compliments on the Slack channel.
Great. Well, thank you for listening, everybody. It's a privilege to be able to talk with you.